Right. Everything's working. Woohoo. Okay, how y'all doing? You're here. That's pretty good, right? Okay. Canal, could you pray for us, please? Thank you. Amen. Thank you. What language was that? Okay. All right. We're ready. Okay, let's do a little review. So there's two kinds of charge in electricity, plus and minus. Like charges repel, unlike charges attract. Large neutral objects are attracted to charged objects. Charge is quantized for any household or normal kind of thing. When you measure the charge, it's always going to be some integer times the charge of an electron. Charge is conserved. If you have a bunch of charge here, you do something to it, you're going to have the same amount of charge. I gave you some examples from particle physics. Okay, Coulomb's law. So this only gives you the magnitude. So K is this, and you really want to remember this part. And then the product of the charges divided by distance squared. So this is just the definition, right, of the E field. You put a probe in the vicinity of some charge, you use the probe to measure the force, you divide by the probe. That's the definition. We use this to calculate the E field of a point charge, which we're going to be using like crazy in the next chapter. And then we came up with this one. And I know mathematically this is the same as this, but it's a completely different concept. Because you use this if you have an E field already set up, then you put a charge in it, and this is the force that the charge feels, right? We're going to use this a ton. Actually, I mean, this, and this we're going to use a lot. So you certainly want to remember them before we start chapter 2. And we're starting chapter 2 today, so you want to make sure you know them now. All right? Okay, all right. So as I promised, what we're going to do today, we're just going to do some problems. So this is going to seem just like Physics 121, which is all right, right? We're just doing, force diagrams. Okay, so we have an E field, 100,000 newtons per Coulomb in the I hat direction. And everybody remember? So I is like X, J is like Y, and Z is like K, or K is like Z. Okay. Okay, so we have an E field going to the right, 100,000 newtons per Coulomb. And by the way, so F equals QE. So E is F over Q. So what are the units for force? What are the units for force from 121? Newtons. What's the units for charge from 220? Coulombs. Coulomb. So right? So E field is newtons per Coulomb. But later on, we're going to have other units for E field. So whatever's convenient, Okay. So the E field causes the 5-gram ball to hang at some angle. What's the charge on the ball? Okay, first of all, is this equilibrium or non-equilibrium? Equilibrium. Why? Well, okay, that's true, but say it a little bit differently.
Moving it is not.
What does equilibrium mean?
It's not accelerating.
Yeah, right? Because the sum of the forces equals 0. So that means that A equals 0. So I mean, what you said, Seth, was fine, but you really want to say it's not accelerating, okay? Okay, so this is the equilibrium problem, which we've done so many of these things. Okay, now, the E field points to the right. So is this thing a positively charged particle or a negatively charged particle? Okay, if there were no E field, what would this thing do? Straight down. Okay, so there is an E field and it goes this direction. So it has to be the charge of the E field. I mean, sorry. It has to be the charge of the particle. Positive. Why? Well, how about just saying this? Right? I mean, right? You know, the force on this thing is to the right. The E field is to the right, so it has to be a positive charge, right? So remember the other day I told you we're going to use this a ton? First example, all right? We're really going to use this a lot, so you really want to remember it. Okay, so right away, we know that the charge is positive, okay? All right, so let's just do it. Okay, so this is a force diagram, right? So, golly, are we experts at this or what? Okay, so what's the object?
Hold on, sorry, we're a little bit lost. We thought we understood. We don't understand. we're confused on why it's like, why it's repelling. So if it were...
Wait. Why did you say repelling?
Or like
It's attracting, right?
Wait. There's only one charge. There's no attracting or repelling.
So what effect is the...
Okay. All right. This is some kind of a charged object.
Yeah.
Let's forget about the E field. If there were no E field, what would it do?
Nothing.
Nothing. So it would be like this. Right?
Yeah.
Okay. Now let's apply an E field. There's an E field in this direction. And what happens to this thing? It moves. Agree?
Yeah.
All right, so look. F equals QE. The E field is to the right. Would you agree that the force is to the right?
Yeah.
So what has to be the charge? Sorry? What has to be the charge? Positive. Now wait a minute. Everybody okay with that?
Yeah.
Everybody? If it were negative charge, what direction would it move? Yeah, because the force would be negative. Okay? I'm glad you asked. I mean, this is a tough class compared to 121, and you better ask questions if you have them. All right? Because you don't want to get lost. So thank you for asking, Adam. You get an A for the day, whatever that means. All right. Okay, so force diagram. So we set up our coordinate system as always. Okay, what are the forces on the charge?
E field.
Okay, so we'll say Fe. Okay, what else?
We didn't get there.
What else? Gravity. So I just said mg. What else? Tension. Okay. All right. Okay. Anything else?
It's been too long.
Yeah, I know. That's why I'm doing this, just to get those brain cells going again. Okay, anything else? Nope. All right, it's equilibrium. So sum of the forces x equals, all right, so what are the x forces with this coordinate system? Okay, what is Fe, by the way? Because, you know, I mean, we're supposed to find the charge. I don't see any charge here.
3 times the E field.
Yeah, thank you. Oops, whatever. Okay, so we have QE to the right, and then what in the x direction? Cosine? Sine, right? Because this is t cosine, this is t sine, yeah? Okay, so we have minus t sine 20. Okay. So therefore, we know that T sine 20 equals QE. All right, let's do that with the Y. What are the Y forces?
Minus G.
Okay, let's do the positive one first. It doesn't matter. Yeah, so T cos 20. T cos 20 minus what, Katie? How about mg? All right, that equals 0, so T cosine 20 equals mg. All right, so we have two equations. So now, I mean, it's pretty much up to you how you want to solve it. I'll show you how I do it. So I like to do T sine 20 equals QE, and then I'm going to divide by T cos 20. And then I'm going to divide this by T cos 20, but T cos 20 is mg, so I might as well just do mg. Now notice, we don't know what the tension is, right? They don't tell us what the tension is, so we got to get rid of it. So the tension divides out. What's sine over cosine? Tangent. So tangent 20 equals QE over mg. And what are we looking for? Q. All right, so Q, so therefore, Q equals mg divided by E times tan 20. Okay? And if you really want to know, that comes out to be 1.78 times 10 to the negative 7 coulombs. A coulomb is a lot of charge, so most of the time we're going to have like micro coulombs and nano coulombs and things like that. Okay.
Why can't you just put them over each other?
What?
Why can't you just put them on top of each other like the T sine 20?
Like this?
Yeah.
Okay. All right, so let's do it. So, would you agree that T sine 20 equals QE? That's a true statement, right? Okay, now, if I divide by A on the left, I have to divide by A on the right, right? That's just good old algebra. Okay, so I'm going to divide this by T cos 20, and I do that because I know the T is going to kill because I don't know T, and I know sine over cosine is tangent, so that's why I'm doing it. Okay, now, if I do it on the left, I got to do it on the right. So I'm going to divide this by T cos 20. But look at T cos 20 equals mg. So can I just put mg? Yeah. And then the t's cancel, and then I get tangent. You don't, yeah. Okay? So we do that a lot. You know, look, you have to have a ratio. I mean, how else are you going to, well, you don't have to. You could have substituted, right? I just think this is easier. All right. Okay. So does this bring back good memories?
No. Good ones.
Okay, so you know the first thing you have to do is figure out the object. Then you have to figure out if it's equilibrium or non-equilibrium. If it's equilibrium, the sum of the forces equals 0. Then you just do it, right? You do this sum of the x's and the sum of the y's. Then you just solve. So, okay. Any questions? Yeah. All right, let's do another one. I mean, are you feeling somewhat confident you can do this? Just got to get the rust out of the brains or what? All right. Okay, let's do this one. Okay, so, you know, we didn't learn a ton in this chapter, correct? So you know there are going to be problems like this on the homework and on the exam. And I admit it, they're not really exciting, but you just got to know how to do it. What can you say? All right, So what is the object?
The top one.
Yeah, okay, so let's just, you know. So there's our 1 nano, what's nano?
10 to the negative 9.
Yeah, 10 negative 9. So that's right, honestly, that's kind of typical. Again, you know, a Coulomb is just, wow, it's an enormous amount of charge. Okay, so the 1 nanocoulomb positive charge is the object. So so what are the forces acting on the 1 nanocoulomb charge? Yeah, so what is this going to do to the 1 nanocoulomb charge? And what is this going to do? Okay, now, how come there's no, are we going to include gravity?
No.
What do you mean we're not? How come?
I don't want to.
Well, first of all, it doesn't even give us the masses. But remember, how much stronger is electricity than gravity?
A lot.
I mean, it's not even worth considering, right? All right, so pretty much, you know, if they don't give you the masses, it's obviously we're not going to use gravity. But, you know, okay. But hey, we did it on the last one though, right? They gave us, it was 5 grams, so you know if they give you the mass, you got to include gravity. All right? Okay. So I'm going to call this particle 1, particle 2, particle 3, all right? I mean, you got to call it something, right? So 1, 2, 3. Okay, so the 2 nanocoulomb pushes it away. So that's F21, and this guy pulls it this way, F31. Okay, now, so is this along the coordinate axes? No. So what do we got to do? What do we always do if a force is not along the coordinate axes? Components. And it's totally your choice, right? So, I mean, I don't know. So let's do this. Okay, so let's see. So this is 60, right? So what's this? 30, all right. Okay, so we know there's going to be some cancellations and so forth. So we got to calculate, you know, just, we want to get the magnitude, right? F21 or F31. So let's do that. So F21, magnitude, which equals F31, correct? I mean, isn't this magnitude here the same as that, even so I didn't draw it properly? You all agree? Okay. So F21 is the same as F31, which is K, Q. Let me just do F21, so I don't have to keep writing things. So F21 is K, Q1, Q2 divided by distance squared. So here you go, 9 times 10 to the 9th Newton meter squared per Coulomb squared. Okay, Q1 is 10 to the minus 9. Q2 is 2 times 10 minus 9. And what's the distance? Centimeter, don't forget to convert. Remember that, everybody? Because we're using meters, you know. So that comes out to be 1.8 times 10 to the minus 4 newtons. Again, it's just magnitude. And isn't that the same as F31? Yeah, right? Because they're the same charge, magnitude, and the same distance. So F31 equals F21. Okay, now look, we want to be smart. We don't want to do extra work. So how does this component compare to this component? The same. All right, so we're going to add. So, all right, so we'll say F21x. So what is that? So 1.8 times 10 minus 4 newtons times what? Okay, I want to get the x component. Okay, first of all, we want 2 of them, correct? So we want 2 of them. Now this is the 1.8 times 10 minus 4, but I want this. So what is it? How am I going to get that? Sine or cosine? So, right? We calculated this, but I just want the x component. So what is the x component? Sine, right? So sine 30 degrees. Now, what's the beautiful thing about this? Here's a 2, because we have this as well as this. But then here's sine of 30. What's sine of 30? You're supposed to know this. You should know those, you know, this. Yeah, half. Remember the unit circle? All right, so this is a half, this is 2, so they basically go away. So we still have 1.8 times 10 to minus 4 newtons. All right? Okay, what happens to the y components? They cancel, right? Because this one is up, this one is down, so they cancel. Isn't that great? All right, so if we want to be fancy, which we do, so the force written as a vector is 1.8 times 10 to the minus 4 newtons in the I hat direction. Right? So that's the whole thing. How do you feel? Confident? This is easier than some of those 121 problems we did, you know? I mean, the only thing that's new, so on the previous one, you know, we use F equals QE. On this one, we just use Coulomb's law. But then it's all same old, same old. All right, any questions? So you'll get to practice those, and that will help you remember all the good things that you did last semester, or whenever you took 121. All right? So expect to see problems similar to that on your problem sets and on your test. Okay, any more questions about any of those problems?
Not necessarily that, but are we going to have lab tomorrow?
No. Yeah, so I'm glad you asked. So the lab syllabus is on Canvas, and look at we're not going to have lab for like, I think 2 weeks, because we don't know enough yet to have a lab. All right. So yeah, we're not going to have a lab for quite a while. So yeah, just look at the syllabus. All right. Okay, so any more questions about chapter 22? All right. So yeah, you know, I come on, these are sort of boring, right? But you have to do them because, you know, it's just an example of Coulomb's law. And you're good at it from 121, so okay. All right, this is what we learned in this chapter. Some basic electric phenomena, right? You know, plus and minus and attract, repel and all that. Charge model. Okay, what's a conductor? What makes a conductor a conductor? What makes an insulator an insulator? What happens in a conductor that doesn't happen in an insulator? Mobility of charge. That's all there is to it, okay? Mobility of charge. Polarization, well, it says right here. Polarization is the attraction between neutral and charged objects. Okay, Coulomb's law. We already know this from 121, right? You add forces. We learned the strange field model, which we're going to talk about the entire semester. And then we learned the E field of a point charge. Any questions on chapter 22? So here's I already talked about this today. Well, I talked about all of these, right? I mean, that's the chapter right there. So know this, know this, know this, know this, for sure, because you'll see it so often. Okay? All right, let's move on. I'm glad we're ending chapter 22 a little early because it's chapter 23 that is the long one and the mathematically fun one. I was going to say mathematically challenging, but I decided to be positive. Okay, chapter 23, which reminds me, So we're going to have some integrals which are going to be really messy. So, integral table. I think you're only going to use, I think you're only going to, I don't know. I think you're only going to use the one on the bottom. By the way, you see that it says 3/2 there? It's supposed to be 3/2. It just didn't copy real well. And then on the right, it's supposed to be 1/2. Yeah, that was going to be a disaster, right? To the 32 power, you know? All right. Okay, so this chapter is all about calculating. And if you like doing integrals, you're going to love this chapter. Well, you'll learn to love them. How's that? You'll learn to love them. Okay.
That's what my calculus teacher said.
All right. We're going to use the principle of superposition. All that means is you add, you know? All right. We're going to calculate the E field of multiple charges. That's just a total piece of cake. And continuous distributions of charge. Now, just remember, the E field is a vector. So when you're adding vectors, what do you got to incorporate? Direction. And that's kind of a pain sometimes, right? Yeah, so, you know. All right, we're going to learn the E field of common charge distributions. We'll talk about a parallel plate capacitor because you use it all over the place. And then we'll talk about the motion of charged particles and dipoles in simple E fields. Okay? So let's review a little bit. Remember we talked about these electric field lines? So these things are just to help us kind of think of the E field. So again, here, this particle is really close to, this charged particle is really close to this. So it's going to have a strong E field, and it's going to point in this direction. So big magnitude, that direction. Now this one's far away, so it's going to have a small E field, but it's going to point in that direction. All right? So the E field lines just give you just like a visual of, you know, where the E field is strong, where it is weak, you know, the direction. It just, all right, it just helps to visualize things. That's all, right? Some people say it's a map, you know. Okay. And let's say we had, here's a negative charged object. Okay. Now, you know we talked about the probe charge. I guess I don't have it on this slide. We talked about a probe charge, right, before. Okay. So here, so the probe charge we're always going to say is positive. Just makes life easy, you know. Just make a decision and keep it, right? The probe charge is always going to be positive. So if you put a little probe charge here, let's say, what's going to be the direction of the force on the probe charge? Towards or away? Away. That's why the E field lines point away. All right, here's a negative charge. You put a probe charge. You can put the probe charge wherever you want to. But what's going to be the direction of the force on the positive probe? Yeah. So therefore, what's going to be the direction of the E field lines? Yeah. I mean, does that make sense or what? You know? Okay. So look at that. We're using this guy again. Woohoo! Right? Because this sets up an E field. You know? Okay. All right. So there you go. Not much to it, right? Okay, so where is the E field the strongest? Close to the charge or away from the charge? Close. And here's why these E field lines are great. So here you have a really large density of E field lines. You know, here the E field lines are spread apart, right? So you have a small density of E field lines. So where you have a high density, strong E field, low density, small E field. Kind of makes sense. So there are some rules for these E field lines, which should be kind of common sense, but let's just go over them. Okay. Well, maybe not common sense. Well, okay. The tangent to an E field line at any point is in the direction of the E field. What? Okay. Now that's here. So what they're saying is, so here's this curved E field, correct? So let's say we want to know the direction of the E field right here. You just draw the tangent line. Okay? That's all there is to it. All right. The E field is stronger where the E lines are closer together. We just talked about that, right? The density of E field lines. there's only one value of E at every point. Well, that kind of makes sense, right? I mean, you know, how could you have one point and have different values of the E field? That would be crazy, right? I mean, the E field, you know, at one point you can have one E field. E field lines begin or end on charges. Now, that's not the total truth, all right? So we're going to revisit this later on. But as far as we know now, E field lines, look at here, it ends on a point. If it were positive, it would begin on a point. So for now, all we're saying is that E field lines begin or end on charges. But just don't forget that there's more to it, and we're going to revisit it, oh golly, two-thirds, I don't know, halfway through, maybe two-thirds way through the semester. So just remember that. All right, yeah, okay. This is nice because it shows you where's the E field the strongest? Yeah, you know, like right around here, right? Yeah, okay. And you see here, right, the E field lines start, you know, on a chart. Okay. Okay, this is called a dipole. What does di mean? 2, right? So this is a dipole, plus and minus. We're going to talk about dipoles, kind of like here and there throughout the semester. All right, dipole. And you can see here, look at it. It starts at the plus, goes to the minus. All right, starts at the plus, goes to the minus. Here's tangent, right? So there's the E field and so forth and so on. Okay, finally, I have a question for you to figure out. So, consider the four field patterns shown. There are no charges in the region shown. So which of the patterns represent a possible E field? That's the important thing. There are no charges in the region shown. So think about it and get ready to vote. There are no charges. Here, just remind yourself, these are the rules. Okay, ready? All right, let's vote. Which one is the only, which one is correct? Let's vote. Okay, wow, all right. You guys argue with yourselves, with each other, okay? So, Canal, you need to argue with these guys, so if you want to move closer or something. So, argue and figure it out. So, you three involve Canal. Okay, I'm going to be a control freak.
Get rid of it.
Okay, argue.
And D, I don't know, versatile and
He's like another kind of thing.
D was actually in the last slide.
So don't, here are the rules.
Okay.
Okay, ready? Let's just kind of, right. Okay, is A possible?
No.
Why not?
2 different directions.
So, yeah, you can't, I mean, it would sort of, it would have to be positive and negative at the same time. What is that? Does that make any sense?
No.
You can't do that. All right? Is this one possible?
No.
Why not?
Because it starts in the middle.
Because what would have to be there? A charge. But they said there's no charges. Correct? Okay. Is this possible?
No.
Why not? Because
It looks weird.
it says they start and end on charges. Well, there's no charges in right? There are no charges in the region shown, so this doesn't make any sense. Okay, how about this one? Is there anything wrong with it? No, I mean, you know, there's some kind of a positive charge over here somewhere, some kind of a negative charge over here, and it's not uniform. You know, that's okay. So that's the only one that's all right. Any questions? It's okay to ask questions. Any questions? Okay. All right. So in the real world, in science and engineering, most of the E-fields that you're ever going to come in contact with can be understood by one of the following models. Okay? So we are going to concentrate on these models. Now notice, okay, we already did a point charge, so we just have 3 to go. But look, what's weird about this? Infinitely long. What? Infinitely long wire. How about this one? All right, so we'll explain that later on, but right now it sounds a little strange. True? All right. Okay, so let's start the easy one first. Okay. I want to do that. So we already did this Friday. This is the definition of the E-field. The E-field is the force divided by the probe. So for a point, here's a point charge. I don't know why it doesn't show. Oh, whatever. So here's a point charge, here's the probe. So Coulomb's law, right? K, Q, Q prime divided by distance squared. There's the force, according to Coulomb. Then we divide by the probe. Goodbye, goodbye. And we're left with this. So we saw that last week. So there it is, all right? So that's for a point charge, okay? And what if we have more than one point charge? What are you going to do? Just add them, okay? Oh yeah, sorry. That's the E-field of a point charge, written in terms of vectors. All right, so now we have more than one charge. So we're going to add the vectors. So we have to include the directions. Okay, everybody. If it were me, I would draw this on a piece of paper, and I would draw the vectors. All right, we want to know the E-field here. And remember, the E-field of a point charge is this. For a point charge, the magnitude is this. So it depends on the distance, you know? Okay, so I would draw some pictures if I were you. So everybody get ready to vote. So which E-field is going to dominate? At point P, which E-field is going to dominate? The plus or the minus? The plus, because it's closer. Okay, ready? You ready to vote? Okay, let's vote. Yeah. Again, because, you know, here's the E-field from the plus. It's away from the plus. Okay, here's our object, right? We want to know the E-field at P. The E-field from this guy is away, and it's big. The E-field from this guy is small, and it's toward the negative. So we have big plus, little minus. We add those two vectors, and it's up. So stare at that. Make sure you understand it. Okay, any questions?
Why won't the two forces be attracted to each other if they have opposite?
No. This is a dipole. We're saying that they're glued in place. Yeah. This is a model like for water or something like that. Okay, any other thanks for asking. Any other questions on this one? Okay, let's make it a little bit more complicated. All right, let's do that one now. By the way, this is a crucially important one. So again, I would draw the picture. Picture's worth 1,000 words, you know? Have you heard that saying before? I'm sure you have. What does the force, what's the E field look like at point P from this plus? Yeah, because you're kind of doing this, right? What does the E field look like from the minus? Now this is supposed to be the same magnitude as that, right? Okay, so what do? You're resolving components, correct? And, well, so what's the answer? Let's vote! Let's vote! Yeah. Okay? So, so this could be represented as this plus that. This could be represented as this plus that. And this cancels that. So you just have these two downs. Okay, so stare at that, because on Wednesday, we're going to do this with like Avogadro's number of charged particles. All right? That's when we start integrating. But it's the same principle. Okay? You're just adding these E fields. Any questions? All right. Okay. So that's how you handle E field, the E field of a point or multiple point charges. Okay? You just do that. But, if you look at what we want to talk about, all right, so that, like I say, that's a point charge, but how many point charges are in an infinitely long charged wire?
A lot.
Yeah, so you have to add a lot of E fields, or how many are in an infinitely wide charged plane? All right, so all I'm saying is we're going to use the same method or theory, we're just adding E fields of point charges, but we're just doing it to like an infinite number of charges. That's all. Right? Okay. All right, so this is how we do it, okay? So this is what we're going to do. So now we're talking about continuous charge distributions, like a wire or a plane or something like that. So we're just going to say, let's say we have an infinite wire. Just pretend that's an infinite wire. Let's say we want to know the E field here. Well, we're going to calculate the E field from this point, from this point, from this point, just keep on going, and we're going to add them all up. That's all we're doing. Now the trick is, the angles are changing and the magnitude's changing, right? But that's really what we're doing, okay? So here it is. So, okay, instead of calling this a point Q, we're going to call it, dq. What's that mean? Like in calculus, what was a dx? Just a small measurement, like a small x, So what we're saying, we're saying this is a point charge, and it has charge dq, little tiny charge. All right? Q, dq, who cares, So that's all it is. All right, so here we go. So what's the E field of here's a point charge, dq. What's the E field? it's a point charge, right? But instead of calling it a Q, I'm calling it a DQ. So what's the E field of a DQ? Using what we've learned. You can just look it up. I mean, we just talked about it a little while ago. Okay, let me ask you this. What's the E field of a point charge? Get a yell. E field of a point charge. No, I want the E field of a point charge. I don't want the definition of an E field. I want the E field of a point charge.
So that the K thing?
K, keep going.
Q over R squared.
Yeah. All right, that's the E field of a point charge. Okay. Now let's say that the point charge, instead of calling it Q, I'm going to call it DQ. So what's the E field of this point charge? You get a yell. Yeah, it's just K DQ over R squared. Does that make sense or what? Now wait a second. So this is an E field from this little tiny DQ. Well, come on. If we're going to call the charge DQ, what should we call the E field? DE. So let's just call this DE. All right. So I mean, we're just playing around, you know. Instead of calling it Q, we're saying DQ. Instead of calling it E, we're saying DE. Now, what are we going to do to all these DEs? We're going to add them together. And how do you add tiny things?
Integral.
Integral! All right? So, I mean, this is not a big deal, right? This is the E field of a little charge called DQ. And we're going to call it DE. And all we're going to do is sum all these guys. Big deal. All right, but this has to make sense. Any questions about this?
No.
So this is what I like to say. The total E field is just a sum of the little guys, right? And the DE, right? And the DE is just the E field of a point charge. That's all. So I mean, it's not all that horrible.
It's going to get worse.
Well, you know what they say, what do they say? What's that saying? I don't know. I mean, it sounds easy, but, you know, the horrible part is when you do it. Huh? Yeah. But, all right. Okay. So, we got to, I mean, this is like, woohoo. Now, wait a second. First of all, what in the world is a DQ over here? Now, when you took your calculus class, what did you have? You know, you had stuff like this, right? Or maybe, I don't know, you know.
Is it like the extra credit we did last semester? So I don't like that very much.
Yes. All right? So, I mean, in calculus, you know, you had, I don't know, you had like dx's and dy's and dt's, right? What's a dq? I mean, how do I integrate over a dq, you know? Okay, so what we're going to have to do is learn how to substitute for dq, because we want to get like a dx or a dy. So that's going to be our first item of business, all right? Okay, now, we may or may not have to substitute for this. You know, like if this becomes a dx plus some other junk, and this has an x in it, you know, then we're going to have to substitute for this too, right? All I'm saying is we have to substitute for this because we want a dx or a dy. We may or may not have to substitute for this. If this is a constant, then we can bring it out, right? But guess what? Most of the time it's not going to be a constant. That's why I gave you this. Okay, all right? Okay, that's it for the day. We're done. All right, so Wednesday, we're going to solve this problem. And I'm going to give it to you. I'm going to give you a piece of paper with all the steps because I want you to understand the method. Because once you understand the method, it's not so bad. Here's a saying I forgot. The devil is in the details. Have you heard that before? So that's, you're going to see that. I mean, this looks so easy, right? So easy. You wait. The devil's in the details. All right, thank you. See you later.
I never trust anything that's easy in physics.